Okay, let me, I guess, get started. So first of all, I guess just to remind people, which I think people know, the project progress reports are due, I guess, Thursday night. So you don't have to blow off class on Thursday to get your project done. You can turn it in just before midnight. Um, and are there any questions about the progress report or anything related to that from in TV land or here? Any questions about the progress report or anything like that? It's 5 pages. You're limited to 5 sheets of paper. Um, and again, what do I most want to see? I most want to see that evidence that you've done something since the progress, since the proposal, and that you have a clear idea of what you're going to do between now and between when you submit it and the end of the semester. So, any questions about projects before I go on? Okay. Okay. Then what I'd like to do is spend today talking about logistic regression. Again, the last couple of classes we were talking about linear regression, and we were talking about how you could use, how you could build models that were kind of the optimal model to fit your data that was a linear, linear, weights, okay, constant coefficient weights on every variable, and how we could use gradient descent search, stochastic gradient descent search, to find the optimal set of parameters for that. And today I'd like to talk about not regression problems, but classification problems. In classification problems, we are given examples, but they're labeled by, into two classes, typically positive and negative. You could be trying to label someone male or female. Is a piece of email spam or non-spam? Is a tissue sample cancerous or benign? Okay. A very common task is, given, you know, um, input records, assign some kind of a label to it. And that's what we mean by classification. Um, and there's one idea as far as how you could do classification based on regression that that may come to mind, where you could use linear regression to do classification, would be in the kind of a following thing. Suppose, let's say, we turned our class names to numbers. Again, that's often a good practice. Typically, we have one class labeled 0 and one class labeled 1. Okay, I mean, again, in classification, we'll see that there's kind of um, the bread and butter problem is a case where you're classifying among two classes. Um, Sometimes we will talk about multi-class classification later in the lecture. But let's think about just binary classifiers where there's two classes. You can classify every you can label every item. Label one of the classes 0, one of the classes 1. Um, and people typically call the positive class, which is probably the smaller or more interesting class, is usually what you call the positive one. So in in a test of uh, cancer versus non-cancer, positive usually means you test positive for something. That means you have the disease. That's the more interesting class. If you're building a spam detector, um, you know, detecting the spam is the more interesting class somehow than the non-spam. Typically, we hope that the non-spam is more frequent We hope that you're kind of detecting the harder thing to detect is in principle the spam. So that's a positive class. In the other two examples, by political party and gender, usually these are about balanced. And for these, I would say the class of what's positive or what's negative is kind of arbitrary. Okay? But the important point is we can assign every class each of the classes a number from 0 to 1, and then try to, predict the label of something through a kind of a regression thing. Remember, what did linear regression do? Okay? If we have, we have some y that is a function of x. If we set y to be the label, which in this case is going to be 0 or 1, you could imagine a world where, you have the points that are positive all have y's equal to 0. The points that are negative all have y's equal to, no, the points that are positive all have y equal 1. The points that are negative have y equals 0. There are different x values. In the course of now trying to do a normal regression, we are going to fit the best line to that data. And in principle, you could kind of think we're going to try to, given x, predict what the class label is. And in this case, any value of x where the value of the regression line was greater than a half. Again, if you think about it, the y values, the class labels, go from 0 to 1. You could imagine building using regression to find the best fitting line here. And then for any x, we would, decide that if x is greater than a half, it is a positive if y is greater than a half, it's positive. If y is less than a half, it's negative. Okay? Does everybody see that how this this kind of classification scheme, in principle works? Okay? If there is a distinction where, let's say, all the positive examples happen to have large x values, and all the negative values happen to have small x values, okay? Then in principle, you're going to get a line fit like this, and this would give you some kind of a classification method, okay? Any questions about that? Okay? What's good or not good about this? Okay, I think this scheme is relatively easy to understand, but what's not good about this or good about this? Does anybody have any comments about this kind of a scheme? Okay. I'm not getting what your complaint is.
I think the error is very high in this line because 3 points.
Okay, so the error you're saying is the error very high. Now note that in this particular line, this actually does a fabulous job on these examples. Okay, does a perfect job on these examples, right? What is the y for each x we get? Kabunk, 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 kabunk. These are all less than a half. These are all going to get classified as negative. Kabunk, 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 kabunk. These are all going to be predicted as having a y greater than a half. Okay, on this particular example, this looks like it does a perfect job of classification. Okay, so what do we like or don't like about this formulation? Okay, does anybody see things that are that are good or not good about it? Yeah. What if we have something in the middle? You're saying, what if x was equal to 0? What would we classify it? At this point, we'd probably, in fairness, say, I don't know. Okay? And that's probably fair. You can imagine a world where sometimes you don't know something. This one would be, if you happen to have x equals 0, you'd be equally likely to call it positive or negative. Right? So what don't I like about this? Well, first of all, do we get a sense of confidence from it? What is our sense of confidence from this? We'd like to know not only is something classified as positive or negative, but we'd like to get some kind of a measure of how certain are we. Again, we decided that at x equals 0, it looks like it's a tie. That's fine. But at x equals 0.0001, our regression line is going to give a value that's greater than a half. It would be 0.5001 or something like that. And we will declare it to be positive. Okay? We would like to get a measure of confidence. How much do we trust it being positive or negative? What is our measure of confidence here? Okay? We wanted a measure of confidence. What would it be? Okay? Ideally, we'd like to have a probability. What's the probability of it being positive or negative? Do we get a probability from this? Okay. In here, it's between 0 and 1. The values are in here are between 0 and 1. That looks a little bit like a probability. But do we get a probability from this? Is the value always between 0 and 1? And the answer is no, it can't, because if you notice that there's a point at which the line keeps going up and the line keeps going down. So this value can get us, we could think of that y label as being a probability-like thing. The predicted y value is a probability or a confidence of it being positive. But it's not a probability because it can get infinitely large or infinitely small. So that's one issue with this formulation. The other issue that's a more subtle problem with this, but kind of important. What happens if I have a point, let's say for x equals 30, which I guess is way out here. Okay? That's this point here, right? It's a positive example out at x equals 30, way out there. Very, very positive example. What's going to happen if I add that to the training data? Does everybody see that this line right now, if we have that point, an outlier like this, okay, it is going to shift our classifier out in some strange way. Maybe it's going to end up, the optimal fitting line is going to look something like this now, okay? And if you think about that, is that a problem? Well, it's a problem in that, first of all, linear regression responds quite aggressively to outliers. And second, it's doing kind of the wrong thing because we already, before we added this point, we would have classified it as positive. This point is not really telling us anything that should be shifting the line very much. Does everybody see? This is actually an easy case. And the easy case should not be the thing that is changing the line, the classifier a lot. Where do we need examples that will shift our classifier? You want to think about where are there examples that will tell us kind of something we maybe need to know more. I would claim that in here, okay, is where we are less certain about things are the examples that probably should shift our classifier. But these outliers, okay, basically will dramatically change the thing. And notice that if we put an outlier far enough away, the line is going to get dragged so far in that direction that eventually this point is going to be considered to be negative. Okay? Any questions about that? Okay? So that's why this formulation using linear regression is kind of natural. It's what I would probably have come up if I was on a desert island and I needed to build a classification method on this. But the people see what the limitations of this are. Okay? The primary limitation is that, you know, that regression lines are kind of predictions of what something is. The kind of formulation that we want for classification is to instead think of a decision boundary. We don't want a line that is going through our positive and negative examples. We want a fence that's going to separate the positive and negative examples. Okay? This line, again, in linear regression, maybe we would fit something like that. What we really want is a fence, a boundary. Okay? Ideally, if we can draw in, if we think of here, what we're going to have is it's not a question of we're trying to predict y out of x. In this figure now, we'll assume we have two input variables, x1 and x2. And our examples are colored according to whether or not they are, positive or negative. The claim is that the formulation we want is to find a boundary between the two sets, okay? And that way, any point on one side of the boundary is going to be called a square, and any point on the other side of the boundary is going to be called a circle. Any questions about that? Okay, so logistic regression is a way of is kind of the right way to apply the machinery of linear regression to classification, where instead of finding the best point to fit the stuff, line to fit the data, we're looking for the best separating line, giving it a training set. Any questions? Yeah.
Can you, like, linear regression, add some, for example, x1 squared or 1 over x2, so we have that straight line?
Okay, so your first complaint, which actually is going to go away very fast, is you're concerned that linear things are straight lines. Now, just like we generalized linear regression to enable us to give us let's say different models, more complex models than just lines, by if we add nonlinear features to our data set, we can end up getting nonlinear decision boundaries. Suppose if we add the term x1 squared and x2 squared to our feature sets. We were given as input x1 and x2. If I add other features with nonlinear terms, like the square of them, I can now fit different, a thing that is linear, a curve that is linear in these things, okay, will not, can be something that's not linear. As I recall, the x squared plus y squared equals 1, that is the equation of a circle, okay? And therefore, once you add quadratic terms to the feature matrix, fitting the best linear function of these quadratic terms is going to give us a quadratic separator. So certainly with logistic regression, we can get nonlinear separators. We just have to be smart enough to add the right nonlinear terms to our feature matrix, okay, in order to do it, just like we were with linear regression. Any questions about it? Okay, so we would like to now still use the machine, and everything we said before about linear regression is going to hold for logistic regression. We talked about regularization, the idea of finding which terms are which are the right features, which are the right dimensions, okay? Trying to reduce the coefficients, this kind of thing. All of that machinery is going to apply to logistic regression as well. Any questions? So what is the idea of logistic regression? It is going to be based on the logic from logistic regression, comes from the Logit function, which we have seen before. The Logit function was a way to take any real variable x and convert it to a probability. If we have the function 1 over 1 plus e to the cx, sometimes I haven't given a coefficient there, but that's fine. Okay, what's going to end up happening? At 0, okay, what's going to happen? E to the cx is going to be, minus cx is e to the 0. What is e to the 0? For the constant e. It's going to be what? 1. Okay, so this is going to be 1 over 1 plus 1 or 1/2. So we get the case of, x equals 0 gave us a half. As x became larger and larger, because this exponent was negative, e to the minus x is going to get smaller and smaller. This is going to approach 1. So the more positive it is, the more, the closer to 1 it is. If x is negative, negative is positive, e to the positive, when you get bigger and bigger, goes to infinity. 1 over infinity goes to 0. Okay. This function has the Logit, as we saw before, does what we want. It turns something into a probability. Now what is the idea? The idea is we are going to want to build again, when I look at the Logit function, it does what we want in that it's returning a probability between 0 and 1. But it only has what looks like one variable in it. We can generalize the Logit function by instead making the value of x. We will take x and pump it through some function h, where h is going to be a linear model on the input. Okay? So now what we're going to do is we're going to use this function, this linear function h of xw. X is going to be the variables, w is the coefficients of those variables. Okay? H of xw is going to come up with a number. The Logit function had the property that for any number, it got mapped from 0 to 1. Okay? And likewise, if we plug this in as the exponent, f of x is going to be a value from 0 to 1 that reflects, the full vector x. There's no, instead of just an integer x. Any questions? So what do we want? Our goal for logistic regression, if we go back to this model, the fitting is we want to fit and determine what these coefficients are. We'd like the coefficients that do the best job for separating. We want to find what is the best coefficients of this line W so that we can separate the points of our two classes. And so in order to do that, we need to come up with what the right scoring criteria is. Okay? We're going to assume that every training example is either positive or negative. Positive was given a value of 1, negative was given a value of 0. We're going to want to score our model by we want to come up with the coefficients W with the property that they give a high probability on positive examples, and they give a low probability on negative examples. Okay? And if you think back to our, how we formulated linear regression, we came up with an error function that was the sum of squares of the points. And we said, find the values of the, find the coefficients that minimize the sum of squares error. Here, we're going to need to have a cost function that is going to, for each of our training examples, come up with a punishment for a cost for our model giving a probability P to an item of a particular class. So what should that scoring function look like? I am going to say that we don't want, if we think about it, we have two cost functions here. At one end, the cost function is 0. This is the cost function, the cost. At one end, the cost is 0. And the other end, the cost goes up towards infinity. What do we want? If the item actually is a training example that is a positive example, a positive example means that its label is 1. If its label is 1 and our model awards it a probability of 1, we are perfectly happy. We say that the item was positive. We say we're 100%, probability of 1 means that we're 100% sure that the item is positive. If so, we did perfectly, and our model should pay no cost. If, on the other hand, our model said that there was a 75% chance, 0.75 chance of it being positive, we should pay some cost, because yes, 0.75 is greater than a half, because our chances of saying greater than a half meant that we, if the convention is greater than 1/2, it's positive, less than a half, it's negative. The item is going to be from the negative class. Anywhere in this range, if the item was positive, we made the right decision. Anywhere in this range, the item, we got the wrong label on the item. Clearly, when we make a wrong decision, we should pay more of an error than when we made the right decision. But also, as we got closer and closer to being wrong, we should pay a cost, and that cost should accelerate the further we are from it. When we got the wrong label, we should pay more of an error than when we got the right label. When we really got the right label, if we felt that there was 100% sure that the item was negative, that's what a probability of 0 was, and the item was really positive, we should pay a tremendous cost, okay? Perhaps an infinite cost for it, okay? And again, the reflection of this holds for the negative case. If it's a negative example, the label should be 0. If we say that the chances of it being positive are 0, and it was negative, we did it 100% right. So long as we said that the chances of it being positive were less than a half, then we would have gotten the label right. But the bigger and bigger probability we gave a positive thing, okay, the bigger positive probability we gave to a really negative example, the more we should punish. If you're following this discussion, what it should be clear is that these curves kind of give you the shape of the error function that you would like. Any questions about that? Okay. It should be clear that there is a separate error function for positive examples and for negative examples. They should be symmetric around the line y equals, x equals a half, and that they should have the basic shape of this. Any questions?
Should this for the sum of these two functions? One equals y equals 1, one equals y equals 0, so we have two. Yeah.
So now what you're concerned with is if I've got two error functions, I don't want both of them to apply at the same time. That's what I think you're trying to say. You're trying to say that if I have a positive example, I've got to make sure I apply it the right. If I have a positive example, I've got to be smart enough to apply the red one for a positive example and the blue one for a negative example. H of x should be the result, it looks like, of the Logit function. So this is assuming a probability. It should be that this is e to the something. Okay? We're assuming that this is a probability. The x-axis here is a probability. Okay? That's what we kind of want. Any questions? Okay. If we believe that shape, then in fact, the logarithmic function turns out to define what the shape of the error function we want. What is the log of 1? The log of 1 is what do I raise, e to the x to get 1? And the answer there is going to be 0. Okay? So log of 1 gives us what we wanted as the value for the positive thing. Okay? That if we have if the item was actually positive, okay, it was 1, if the probability was 1, log of 1 is the correct cost for a positive item. If log of 0 is minus infinity, okay, now negative log 1, okay, negative log of 0 is going to be minus infinity. That says that when we have a positive example, okay, and we scored it as the probability of being positive is 0, we want to pay an infinite cost. Taken together, minus the log of the Logit function applied to our model, okay, is the right way to punish a label that was truly positive. And if we want to kind of get to the reflection of this thing, reflection turns out to be 1 minus what that function was. Okay, for the negative examples, okay, we want to flip this cost function around, the axis of, of x equals 1/2, the way to do that is simply to make it 1 minus f of x. And this is the right cost for a negative example. Any questions about that? Okay. Taken together, what do we now do to get the cost function for the Logit thing? Because we know that, our labels, because we cleverly defined our labels as 0 to 1, we can turn these partial cost functions into a real cost function simply by multiplying each one of the error terms. This was the error term for a positive thing, right? The log minus of f of x. That was the error term we want to pay on a positive example. If positive examples had a label of 1, if we multiply y of I, if y of I is going to be the label of the item, y of I is either 1 or 0, depending upon whether it's positive or negative. If we say y of I times the punishment for a positive example, this does exactly right. It's 1 times the error for the positive thing. And if we have a positive example, y of I is going to be 1, and 1 minus y of I is going to be 0. For a positive example, this term is going to be non-zero. This term is going to be 0. And that tells me that if we have a positive labeled example, we are going to pay the penalty of this. This is the label for a penalty for a positive example. This is the penalty for a negative example. And so if the item was positive, that would be y equals 0. It's 0 times the positive penalty. It's 1 time, if it was positive, yi was 0. Was 1. Yi was 1. 1 was the label for the positive. 1 times the positive error term plus 1 minus 1 or 0 times the negative cost. On the positive example, we're only going to pay the positive cost. On a negative example, that meant y of I was equal to 0. 0 times the positive cost plus 1 minus 0 or 1 times the negative cost. We will pay the negative cost on the other example. The great thing about this is this now gives us a simple, algebraic formula to govern the error in our classification scheme. If we have a particular logistic regression model as defined by these weights W, okay, how good is it? Well, we're going to get the probability from that model on each positive or negative example, and we will score it according to the appropriate thing, and the sum of these error terms is going to govern the error of that model. Any questions about that? I find this a clever thing. We're using the labels as kind of indicator variables to turn on or turn off the wrong error function. Any questions? So what is logistic regression then? Well, we now have an error function. We have a set of weights that we want, okay, to find the best one, the one that minimizes that error function. It turns out that this error function is a convex error function. And because it is a convex error function, We can find the parameters by gradient descent search, okay? And in the course of finding that, we will find the best linear separator between two classes. Any questions? And as I said, it's linear in features that might be nonlinear. So you can, in principle, if you're smart enough to put the right features in, you can find the best shape of, the shape that you want. Any questions? Okay. Any questions about that? So here is an example of logistic regression in action. I took data where I took people as points in height weight space, and the label was gender. Are they male or are they female? And generally speaking, women are shorter and way less than men. Okay, this was the optimal decision boundary. This line over here represented the optimal separator found by linear regression in separating the men from the women. It didn't do a perfect job because there are short, lightweight men and there are tall, heavyweight women. Okay, here might be an example. Okay, but it turns out that in the red region, which is the stuff below the line, it looked like there were 230 positive examples and 60 negative ones. So something like 3 out of 4 of them were women, and a similar amount of them happened in the region above. About 3/4 of the people were men. Any questions? Okay. Any questions of how we can use linear logistic regression to find a separating boundary, a binary classifier between two things? Yes.
If W is error function.
What was that?
J of W.
J of W was the error function. Yes.
Okay. So we need to calculate the derivative of gradient.
Yes.
Okay. But my problem is the Logit function has zero near very near zero derivative when x is pi. It's like a line.
Say that again.
Logic function.
Yeah.
Logic function is a boundary is like a line. So the derivative is going to zero. Logic function.
Here's our Logit function.
Okay. At that end and this.
Yeah, at this end, the derivative is 0.
Yeah.
And at that end, the derivative is 0.
Okay.
It goes to 0. It isn't actually 0 until you get to the, this is something that is asymptotically approaching 0. It's getting close. The derivative is going to get closer and closer to 0.
Okay.
But it doesn't reach 0 until it gets out to the, infinite values.
So the features that are boundaries are not important on J of W when we calculate the gradient.
Well, right. Okay, so the question is, when you take the derivative of this thing, okay, here was our function. Your claim is that when we really, well, note that the gradient that we're taking is, we want it to define, okay, so let's just remember what we're trying to do. We are trying to minimize this. We want the derivative of this. This is not the Logit function.
Yeah, but when we take gradient, it's f prime over f.
Yeah.
Right? And f prime goes to 0.
Okay, we agree that if you were at a point where, you know, what you call it, that the value here was extremely close to 1 or 0. Let's say that there was no error. When would we want the derivative to be 0? We would want the derivative to be 0 when there was no error on any of our classification. That meant that we gave a perfectly probability of being positive, of being exactly 1 for every single example, and negative for when it was and a probability of 0 for every single negative example. That means that we do want the derivative to be 0 in the case that a positive example was labeled with probability 1, and a negative example was labeled with a probability of 0. So you want, in some sense, the derivative is going to be flat on the logit exactly where we're doing the perfectly right thing. Okay? So I think this is doing the right thing. Okay? Any questions? And of course, realize that if you're ascribing, one thing with this mention is that your model is describing a probability of, getting a cost function, an infinite penalty for giving a probability 1 to a, to a negative item. Now, that's a pretty big penalty. So the best fitting model is not going to want to do that. The best fitting models are going to be a lot more conservative and not want, to ascribe something to have a probability of 1, even if it was positive or even if you were very, very confident. You want it to be high, but you probably don't want, the best fitting model is probably not going to assign it something that will take this term to 1 or 0. Because if there was any chance of misclassification, it pays a very high penalty. Okay? Any questions? Okay. So what is good about this? We have a way to use logistic regression for classification. What what else did we have to worry about? And there are a couple of some other issues that go on to get involved in building good classifiers. One issue to note is that if we're using logistic regression, what is going to happen? What would be the optimal line if we had one positive example and many, many negative examples? What should, you can imagine that this is what our world looked like, and you wanted to come up with a line that was the best separator for this on our training example. What would the best separator be? You kind of see what I'm saying now? You've got an example of one type over here, one single point in isolation. You've got a lot of negative examples out here. Certainly you can draw a perfect classifier here that never makes any mistakes, right? You can drive a truck through this one, right? Does everybody agree that that's a separator that doesn't make any mistakes? Does this separator make any mistakes? No, none of these separators make any mistakes. Which is the one that logistic regression, first of all, which is the one that you would like as a separator in this case? Okay? Does anybody have a preference to what they think the separator should be? You would like it to be, you may say, I think what you're saying, okay, is that you want that to be the separator. Is that the right? Would you like that to be the separator? Would you like this to be the separator? Or would you like this to be the separator? You're saying you would like A to be the A, B, or C. These are three different kind of ideas for what might be the optimal separator. Logistic regression is probably going to like A the best. Why? Recognize that that it comes up with a penalty for you get credit for the more positive you classify the positive examples. The higher probability you classify the positive examples, the more points you get, the less error you get in the model. In this case, there is only one positive example here and a million negative examples here. My claim is the model will probably be happy with line A. Why? It is getting a big reward for saying, look how far, okay, the negative points are from the boundary, okay? It will get a little punishment for having this one example B be kind of close to the boundary, okay? But if we have very, very unbalanced sets, okay, logistic regression is going to pick A. What would we want the separator to be if we had an equal number of positive and negative examples here? Okay? I think most people will say we want B. Okay? Generally speaking, I think B is actually a better separator, even in the sparse case. If you're asking me, what would I want my algorithm to come up with? Okay? I kind of like the idea of there being a big separator between the positive and the negative ones. You want to classify the labels right. That's usually your primary goal. The farther the boundary is from your examples, the more cushion you have in getting it right. Okay? Generally speaking, if you have, under the logistic regression criteria, if you have unbalanced examples of one positive and a million negative, the line is going to hug. Again, let's get rid of these. Sorry. If it's unbalanced, the line is going to hug, try to get as far as it can from the main body of the examples. Okay? And that I don't think is kind of really what we want. How do we fix that? The best way to fix it is by having an equal number of positive and negative training examples. And then it tries to kind of put the line in the middle of them. Any questions? So our dream is that if we're doing this classification, we want our classification to be, our sets to be balanced. So how do we go if you have a classification problem and you've got a majority class with a large number of elements that is much larger than the minority class? How can you balance it? Well, one way to make, if you have a lot of positive example, one positive example and a lot of negative examples. So let's say a few positive examples and a lot of negative examples. One way to make it balanced is to delete, okay, a lot of the negative examples, okay? So you could imagine a world where if you have one much bigger class than the other, one way to balance it is simply to delete the elements from the bigger class. Another idea is to weigh the minority class elements more heavily. So if we have in a world where we've got 100 negative examples and 2 positive examples, if I weighed each one of my positive examples 50 times more than one of my negative examples, then in fact the separator between them is going to be in the middle, which is kind of what we want. Okay? So one idea that in general, that is often a good idea, is to, weigh the minority class elements heavier, so the total weight of the two classes is the same. The good thing about that is that now classes are balanced effectively. The weight of the classes is balanced. The bad thing is that the two positive examples here, okay, if they are not representative of the full elements of the positive class, are going to be weird, and the model is going to try very hard to fit these two weird examples. So there's a danger of overfitting. Another way to deal with unbalanced classes, if you have a world where you have 100 negative examples and 2 positive examples, one possibility is simply to make copies. Sometimes your solver will let you assign a weight to each example. Another example is simply to make more copies of the positive examples, okay, until you have the same number of each type, okay? And now you've got a balanced thing. Now the classifier is, even if your classifier machinery does not allow, your program does not allow you to weigh the examples. By replicating the examples, you will get equal weights of the two classes, and quite likely the model you get is going to be better, although it has the same risk of overfitting as before. Any questions? And one other idea, that if you're replicating the examples, maybe it's better to replicate them with noise, okay? Add some kind of random perturbation to the elements that are positive so that you can generalize it by creating essentially synthetic positive examples rather than perfect replicas. If you do this in the right way, maybe you can get you can avoid some of the overfitting problem, okay? Any questions? So balancing classes is an important thing. Dealing with multiple classes, more than just binary classification, is also an important thing. If you want to classify a movie, okay, often you have a world where movies have into genres. Movies can be comedies, drama, action. That's a representation of a multi-class classification problem. Okay, you could, so here is an example of a 3-class classification problem. Okay, any questions? Now, what would we like to do? In principle, for the binary classification problem, we wanted to find a separating line. For the multi-class classification problem, ideally, you may want to do something like that. You'd like to find a separating division of in feature space, so that all the elements in one region of feature space get the same label. Okay, but it's not clear. But we can't do that with just one linear separator. It's clear that there's several lines involved. Any questions? So how can we encode multiple different classes, okay, if we're going to solve a multi-class classification problem? We saw that we could have, before we represented our positive example as 1, that was positive, and a negative example as 0. We might think about trying to represent multiple classes by having multiple different values here. Let's say I wanted to classify people into what their hair color is, okay? You could imagine having 0 represent blonde, 1 represent brown, 2 represent red, ... What's a limitation? What makes it a bad idea to encode multiple classes by 1 variable? What is a consequence about, let's say we're encoding hair color by a variable. What is the property that we would want the numbers to reflect? You might imagine blonde equals 0, or for people who have very, very light hair, right? Maybe you might want to say black equals, let's say, 10, represents people who have very, very dark hair, right? If we view hair color as a continuous number, okay, then that gets us into a regression world, okay? If we are trying to represent discrete and classes by things, unless the classes are kind of linearly ordered, it doesn't make sense to assign one numerical variable the weight of the class. Hair color does not seem to me to be linearly ordered, okay? There's not a continuum from light to dark, from light to dark. Where's bald, okay? Bald would seem to, I don't know where bald fits in on that continuum. I don't know where gray fits into that continuum, okay? If you don't have a, a linear ordering of the classes you're trying to do, assigning one class variable for it gives a numbering that is meaningless, and trying to carve that up doesn't tell you anything. Sometimes there are classes, multi-class classification, where things are linearly ordered. If you want to rate how good a movie is, there are movies that get 1 star, 2 stars, 3 stars, 4 stars. Those are, you can think of that as 4 discrete classes. But there is a linear order to those classes. A movie with 3 stars is more like a movie with 4 stars than a movie with 1 star. Okay? A Likert scale is kind of when you're trying to, you have people kind of forced to make discrete choices of classes. Okay? But there is still an ordinal ordering of those classes. Okay? You know, when you're asked on a poll, do you agree with something completely or completely disagree? There is a range of things. You could think about a classification problem as predicting the individual class somebody was going to answer, or you could think of it as you're better off in some sense viewing ordered classes as regression problems. Okay, because in a multi-class problem, the default thing is either you get the label right or you get the label wrong. In an ordered class problem, there are, if the right answer was mostly disagree, and you picked slightly disagree instead of mostly agree, you should get partial credit for this. And that's, not the case in a general classification problem. Any questions? How do you deal with, multiple class classification? We know using, using logistic regression, how to build the right binary classifier, okay, where you've got 2 sets of things, okay? One way to solve multi-class classification problems is to create a multiple binary classification problem using a 1 class versus the rest. Suppose we have a world where there are 3 classes, triangles, crosses, and boxes. We could label the world into triangles and non-triangles, boxes and non-boxes, crosses and non-crosses, and train a class separator, okay, for each of these 3 cases, okay? Then how would we decide what the class for something is? Well, for each one of these, if we did a logistic regression, for any point, okay, this is the point over here. For any point, we get a a probability which is a function of how far is that value from the separating line. You could imagine for each one of these three, in this case, three classifiers, for any example, we're going to get three probabilities. What's the probability it's in A? What's the probability it's in B? What's the probability it's in C? Selecting the highest probability, okay, is a way of getting a one versus all class, a single label out of these K different binary problems. Any questions? So the good thing about using the one versus all classifier is that we can generalize logistic regression to multiple classes. The bad thing about it is that multi-class classification is a much harder problem. The more classes you have, the harder it is to get the right class, okay? As we said before, if you've got K classes and you're just going to guess, okay, the probability of getting it right that the monkey would have is only 1 out of K. In binary classification, the monkey will get it right half times. If you have 1,000 classes, the monkey will get it right only 1 out of 1,000 times. Okay? So how do we do better on the very, very hard case when we have large numbers of classes? One idea is to look at, is to realize that when we have many classes, okay, certain mistakes are probably better than other mistakes, okay? If you're classifying images into something, if I see a truck, I'm happier calling it a car than I am calling it a person, okay? So we would like to, in a multi-class game, we often want to try to organize the classes in a way that classes that are similar, okay, even if we get something wrong, we're likely to get a similar class from it. The other problem that comes up with multi-class classification is that if you break the world into 1,000 different classes, usually there's some kind of, I won't say power law thing, but it's often the case that rare cases become very, very unlikely to happen. And you need to kind of, adjust for those kind of probabilities. So these are the two issues that come up with multi-class classification that we haven't seen. Certain classes mistakes are more acceptable than others, and rare classes, often become exceedingly rare, okay? Any questions? So one way to deal with, to make it more likely that when you have a multi-class classification problem, when you have a large number of classes, you don't make really stupid classifications, is to simplify the problem by reducing the number of classes. If you can take your classes, okay, in this case, and build a hierarchy on those classes, okay, then what is the situation? If you want to classify what kind of, in this case, food you have, if you have classes of things as meat, fruits and vegetables and grains, recognizing something as, being a pork belly versus lamb is a fairly subtle decision, okay? If you arrange your classes in a hierarchy, you can build a classifier at the root level to distinguish between the higher order classes, okay? Group all the representatives of all these classes into the next higher level, okay? And then build a classifier that to make the decision of what the label you want is, first decides the basic group, okay? And then once you have a basic group, then does a split between a smaller number of classes. Grouping classes by similarity makes the problem easier because you get smaller number of choices at each time, and the penalty for going wrong, okay, diminishes as you move down the hierarchy, okay? So we are often happier with a close call in here than we would be if you labeled something bacon that was really spaghetti, okay? Any questions? ImageNet was is a famous, kind of test bed and problem in computer vision. When I looked at this thing, there were 27 categories of things, okay? But there were 21,000 subcategories. If you wanted to try to guess what something is, okay, your problem is much easier to try to figure out which of the 27 high order categories were you in, and then keep going down rather than try to handle this with 21,000 separate, one against all classifiers. Any questions about that? Okay. This, by the way, is how do you come up with these taxonomies? Suppose you are given, just these 21,000 categories. How would you break them up into a smaller number of super categories? What kind of a problem is that? What? Clustering. And that's one reason why we're going to talk about clustering in the next, in the next week or so. Okay? That's an example of where clustering is a useful thing to do. Any questions about hierarchical classification? The second problem that comes up with this kind of thing is that when you're doing a classification problem on 21,000 categories, okay, it is often the case that certain categories are going to be very, very rare when you try to do the classification. You can imagine in the ImageNet problem, you've got some pictures of pandas, okay, giant pandas, and you've got some pictures of cats or dogs, let's say cats. And to a first approximation, a panda doesn't look that much different than a cat. I mean, you can different, but it's not unbelievably different. But you could imagine a world where if you built something that had to classify images into 21,000 categories, if you don't have an idea that pandas are rare relative to cats, you will end up, calling, if you were running an image classifier and anything that you see out there, you will end up classifying a lot of cats as pandas. So this is where the idea of using some kind of a Bayesian prior is kind of an important thing. Remember what Bayes' law was. Bayes' law said that the probability of the label A given the evidence B is, okay, B could be considered the evidence B is the vote of a classifier, okay? Suppose I look at a picture and I say this is 93% chance of it being a panda, okay? P of A was the prior probability. What's the probability of a picture I take being a panda, okay? If you know that, if you're looking out around, if this photo was taken in the United States, your probability of seeing a panda is near zero, okay? That has got to dominate the fact that, what your classifier is. So Bayes' law gives you a way to correct for that kind of probability, okay? Again, it was showing how much do we update the probability where pictures had a certain probability of being panda to begin with, in light of the fact that we had this evidence, okay, that it was from the image classifier. Any questions? And I will say, making the corrections for prior probabilities is unbelievably important when you're doing these kind of classifications. We once had a task where we were trying to classify Wikipedia pages by what job title they had. And again, there are a very small number of people in Wikipedia who became presidents, okay? And it's or became rock stars. There's a lot more that became other things. And if you don't adjust for that, you end up overclassifying people in these rare classes. Any questions? The final thing I wanted to say about logistic regression and the multi-class classification is, as we said earlier in the semester, if I'm doing a one versus all classifier, okay, I can then, from logistic regression, I will be able to determine what's the probability that X is labeled A, what is the probability that X is labeled B, what is the probability X is labeled C, okay? If there's only three classes, by default from these one versus all classifiers, there's no reason why these probabilities should add up to one, okay? What you need to do is, if you want to turn them to real probabilities, you have to basically make these probabilities, if the probability of being in each of these classes sum to one, you've got to do some kind of a normalization for that. One way to do it is a linear normalization, where basically you just sum up the observed probability. If this was a probability of 0.8, this was a probability of 0.3, this was a probability of 0.2. You sum it up and get a total of 1.3. And then you divide all the probabilities by 1.3. Now the sum of this divided by 1.3, 1.3, 1.3, that adds up to 1. Any questions about that? Okay. The other normalization of this type that people use is something called softmax, okay, which we talked about earlier. We could instead normalize it as e to the, x divided by the sum of e to the y for all possible labels y, okay? And this would again have the property that it's going to normalize it, so the sum of these things is going to go over all different classes, will go to 1, okay? And that's a different way of scaling. Any questions? Any questions about multi-class classification? Any questions about the project proposals? Again, they will be due at midnight on Thursday. Okay? But if you want to talk about your project, I'm going to go to my office hours now. Any other questions about projects? Okay, thanks for your attention, and I will see you next class.
How do we update probability using Bayesian law?
How do you update the probability using Bayes' law?
For example, I get
do
a regression, and then what should I do for
what is the situation here? Again, how would you update it? Okay, using Bayes' law. Well, let's think about this. Okay. Certainly, first thing is we believe Bayes' law. So if we have these four terms, we will claim this is the right way to do it. Now, what is this? What is the situation? Here, we want to know what's the probability. The example of this would be kind of something like, what's the probability that X is a panda given, you know, we
Some features.
call, you know, it a panda in our classifier. Right? That's kind of what's going on here, right? The first one of these terms, that's what the target is here. This first term, the prior, is what's the probability of it being a panda? And that you kind of knew from, what you call it, you know, what you call it, you knew from counting how many pandas there were in the world, right? This is the probability that we would call it a panda, right? That given an image, we call it a panda.
Okay.
And what would this be? Well, if we trained our classifier where we had an equal number of images of each type, probably this is something like 1 over the number of classes. Right? Now, then there is this thing. What is the probability we called it a panda? Okay? This is a thing. What is the probability we called it a panda,
If it's really
given
a
it was a panda? And this is kind of the accuracy of the classifier, right? And what does that work out to? Well, that's probably, I'm going to guess, something like, you know, maybe like 0.8 or 0.9, something like that. How good are we when we call it a panda, that it really is a panda? So this is how we would update it. These terms, we can certainly estimate a lot of these terms. You know, these other terms we can estimate, okay, in sensible ways.
And another question about the example that we have 1 plus and many minus.
Yeah.
Okay, you said that you prefer a line between them.
Yeah.
But I think in this problem, C is better because it's very dangerous to this only one example.
Okay, so this is now a taste question. To a certain extent, there are taste questions here, which you like better, right? If you like logistic regression, this is what logistic regression would do.
Yeah.
Okay?
But I personally prefer this one because this is only one, and we are interested in this one, for example, cancerous.
You know, you are, if you're saying you like this, recognize that you're saying that all this term is non-cancerous, right? This is the negative one.
No, for example, this is cancerous, not non-cancerous, because as you told,
Okay.
the cases we are interested in almost always rare cases.
Okay, positive is usually the rare. Okay, this was positive. Fine. Okay? But what are you doing? If you're drawing this line, you're saying that all of this is going to be cancerous. And I guess, you know, conceivably you'd like that. But you're giving an awful lot of weight on this one example.
Yeah.
Do you see that moving the line over to here is giving, you know, more weight to this than to all of the 1,000 of examples?
Yeah.
Okay? So, you know, you're saying if you want to be really conservative, you would pick that line.
Or at least, for example, something between B and C.
Okay, if you like support vector machines, the support vector machine would pick this one. So that's going to be one of the differences. We'll talk about that, I think, if we get time. But the logistic regression would pick here. Support vector machines would be here. You want to pick here. And if you really believe that, then you probably need a different cost criteria. Okay?
I can't do this by weighting this one.
You probably could, but what would you want to weight it as? I guess if you weighted this as
J of W.
If you weight this thing very big, that's going to drive the line in logistic regression over. So if you're telling me you want to be really sure around this one, that's the equivalent of ascribing a bigger weight to those positive examples. And that would do it. Okay?
Okay.
Okay, fair enough.